Hello and welcome again. My name is Łukowski, and once again I have a pleasure to host my friend Don from Credo. Today we would like to share something really exciting with you guys. And as you remember, last time we've been going over very unique portfolio which Credo represent, and I was pointing that really something which let's say was stealing my heart are the breakout cable, the 400G to 4x100G with the gearbox, because this is something that we really need in our open networking. And in general, if you wanted to split the 400G today, basically you are going over the transceivers, which is one of the way, or we have a really nice solution from the Credos. That was excellent for me. And it was a pleasure to listen it and witness what you've been able to present. But how about today? How do you see our, let's say, event today from the agenda perspective?
Sure. So today we're going to talk about NIC to TOR connections and a mechanism that we developed with Microsoft Azure to move from a single TOR to a dual TOR and manage the whole thing from the network side. So the compute side is not even aware that it's connected to dual TOR, but it gets all the benefits of redundancy and higher reliability from doing so. So we'll walk you through kind of the learnings we went through, the product we went through, the upstream support we have in Sonic, and then we can talk about the integration and some of the value that STORDIS can provide.
Perfect. And how long you been working on that technology to right now, be fully ready?
We actually started it just before COVID. So we started it in December of 2019. And I do recall at one point during the COVID shutdown that we may have moved the entire rack into my garage and plugged it into my dryer outlet to keep it going. So it was not a dull development, but we started about just over 2.5 years ago, and it is now in full production.
Perfect. Really looking forward.
Excellent. Well, let me start here. A little message from our legal department. Make sure you read every word, and then on to the main show. So a traditional rack in a data center has a single top of rack switch, which connects a number of servers to the network. And that top of rack switch represents a single point of failure for that rack. If that TOR fails, then the rack goes down. And Microsoft published a paper which is actually linked in the handouts that you can find on the right side. And they did an analysis of their fleet of TORs, and they found that TORs actually do fail. So they were losing about 2% of their TORs in the first 3 months. And when they said lose, that means experiencing some sort of an outage. So about a third of those were due to hardware failures. Approximately a quarter of them were due to power failures, and the rest of them were due to software issues. However, any of those issues, even if it's only for a few minutes, takes down that entire rack and creates a real reliability issue for their customers. And they found that this was the #1 reliability issue in their cloud infrastructure. So it became a high priority thing to fix. The classic solution to this problem is to go to dual TOR with something called multi-chassis link aggregation, or MLAG. And so in this case, you install a network interface card that has 2 ports on it inside your server, and you connect that up with 2 of those orange cables that you see. And then you connect the 2 TORs together with another cable called an interswitch link. And so this is something that's been around for some time, and it's actually something that Microsoft deployed until about 10 years ago. So there's a couple things that limited their deployment of this. So the first is that capacity planning on this interswitch link is problematic. You have to think of the various cases of failure and traffic and decide how much of the TOR radix to dedicate to the inter-switch link. And they found that this had to be customized to each application, which is very much not what you want to do in a generic cloud environment. The other challenge is that inter-switch link is really important for keeping the state of the two TORs together. The two TORs are trying to constantly figure out who is in charge and if they're both healthy. And if that inter-switch link fails, then the two TORs can both think they're in charge and you get something called a split brain problem, which can bring down the entire rack. So as you dig into this, there's also some dependency on the server. So that large gray box on the right-hand side is the server. And so you have a NIC that has 2 ports on it. Both of those are linked up to different TORs. And so to make those 2 ports look like one to the guest OS, to the Docker container or the virtual machine that's running, you have to run some software, typically a hypervisor and running vSwitch or OBS. And what that hypervisor is doing is it's combining those 2 ports together and load balancing them and figuring out what traffic should go where so that the VM doesn't have to do that itself. And traditionally, it's doing that on some of the x86 cores. When we had 1 gigabit or 10 gigabit network connectivity, that was okay. You can shuffle about 2.5 gigabits per second per core. So maybe you use 1 core or 2 or 3 or 4 cores to do so. As networks have gotten faster, that hasn't scaled well because, as we all know well, x86 processors and cores are not getting much faster. And so you're consuming too many of the expensive resources to do that. You also get quite unstable latency. You get quite a bit of jitter on that link because it's shuffling things back and forth, and you're not able to support the remote DMA use cases all the way to the guest OS through this. Intel developed a technology called single root IO virtualization that many of you might be familiar with, which allows a network interface card to basically present multiple copies of itself so that each guest OS can see its own version. And so the benefit of this is it has the potential to bypass that hypervisor, which is exciting. But the downside of it is it kind of kicks the problem to the customer. So now, rather than having a hypervisor that's run by the cloud infrastructure provider, which is managing these convergence scenarios in the case of a TOR failure, the end user just sees 2 NIC ports and sees 2 TORs and has to manage the convergence himself. And then if you have a TOR failure, the end user is very much going to see it. And so that's not ideal because you really want to hide that complexity from the user as much as possible and avoid them having to put hardware-dependent NIC drivers in their VMs. There are some offloading options. So some of the newer smart NICs have the ability to do some of these teaming and vSwitch functions. The challenge is there's not any standardization on how to do this. And so each NIC vendor kind of does their own thing, which really, if you pick one, you're very much limited to one NIC vendor. And then you again have to put those custom NIC drivers into the VM, which creates a dependency on your guest OS that you'd like to avoid. And so if you look at this system, there's been lots of options here. And so we've got options kind of on the networking side with the inter-switch link. We've got options on the NIC card with the dual port NIC, which is very common. The host OS, either with some form of a vSwitch or OBS or SRIOV, and then the guest OS. But the thought and the discussion that we had with Microsoft is nobody's done anything on the cable side. What if we could pull this complexity into the cable and make life a lot easier for everyone? And that was really the genesis of this Switch AEC product and then the supporting software infrastructure that we jointly developed. So what does this look like? So Credo developed a cable, and it's not a traditional active electrical cable. It actually has quite a bit of intelligence in it. We call it the Switch AEC. And so this Switch AEC is a 3-ended cable. One end plugs into a NIC and the other 2 ends plug into TOR A and TOR B. And it manages an active standby configuration. The cable itself, inside of the connector of the cable, is actually able to manage that failover operation. So the cable is either directing traffic to TOR A or to TOR B, And the cable can drive that switch, and it can drive it almost instantly because we are terminating PCS on all three ends. It's a digital switch across. So it's just essentially a single frame drop when you switch across. The second thing that we added to this cable, which was non-traditional, is we went to a common control plane. So many of you might know that traditionally high-speed Ethernet cables have an I2C control bus on them, but that control bus only controls the local end of the cable. In this case, you can come in from any end of the cable, either the NIC or the TOR sides, and you can access all of the functionality of the cable, all of the telemetry of the cable, and even do a full hitless firmware update to the entire cable from one end. And so this allows it to be entirely a TOR managed device and means that the NIC doesn't have to participate in it at all. The key enabling piece that Microsoft brought to this equation is the Dual TOR management container, which they upstreamed in the November 21 release of Sonic. And so this manages the switch AEC and the control plane there. We contributed a bunch of code to that, as did Microsoft. But then even more importantly, it manages the convergence scenarios in failover using all sorts of standard devices that I'll walk through in a second, ARP, BGP, and then VXLAN and CAP and forward. This is free and open source, and it is available to the Sonic community today. So if we look at this, the legacy link aggregation solution has these disadvantages that I talked about: the inter-switch link, the potential for a split brain on the TORs, the performance issues associated with vSwitch, or the guest OS complexity issues associated with SRIOV. The net result is you have a failure convergence time, which is typically measured in seconds. So if you lose one of those TORs, you're typically going to have an outage that lasts for 3 to 5 seconds. The solution that we developed with Microsoft does not need an inter-switch link. The state is actually held exclusively in the cable, and the TORs are actually measuring that state, which I'll get into in a second. So there's no opportunity for split brain because there is only one brain here. It's the cable. The servers are not involved at all, and so you can run any software or any hardware on these servers. You don't even have to change your server image to do this, which was really, really important for them because you can manage how many, you can imagine how many server images are operating inside of Azure today. And the result of this solution is failure convergence in milliseconds. So in about 50 milliseconds, this solution converges in the event of a TOR failure, approximately 100 times faster than a legacy MLAG solution. So how does this all work? Let me get into the nitty-gritty here. So if we dig into the cable, that blue box in the middle is what's happening in the cable. You can think of it as a MUX. On the left-hand side is the network interface card, and on the right-hand side we have two TORs, the top one being the current active TOR and the bottom one being the current standby TOR. So the northbound traffic coming out of the NIC, the broadcast traffic from, or the traffic from the NIC, is broadcast to both TORs all the time. You can see in the blue lines, the NIC traffic is broadcast by the cable to both TORs, meaning both TORs hear everything. The southbound traffic is muxed, so the active TOR traffic goes through the cable and is received by the NIC, and the inactive or the standby TOR traffic is simply terminated and dropped inside of the cable, kind of a classic MUX behavior. So the way that this works is via ICMP pings, which I think we're all familiar with when we're trying to fix our darn router at home. So what's happening is the two TORs are pinging the NIC at relatively high frequency, about every 10 milliseconds. And so TOR A is the active TOR. And so when TOR A sends a ping to the NIC, it goes through the cable and it's received by the NIC. And then the NIC learns the MAC address of TOR A and it responds to that ping. And so TOR A learns the state of the switch AEC by hearing a successful ping go through. And he's doing that about every 10 milliseconds or so. TOR B is also pinging the NIC, but the southbound traffic from TOR B is dropped. And so TOR B does not get a response from the NIC. And so TOR B understands that he is not in charge. However, TOR B can hear, he can sniff the pings that are coming back from TOR A, and he can understand that TOR A is healthy and that TOR A is in charge. So once we get through that, when the NIC is sending northbound traffic, he is tagging the northbound traffic with the MAC address that he learned from the ping commands. So the NIC sends the traffic tagged with TOR A's address. It's received by TOR A, and TOR A knows to forward that because it has the correct destination MAC address. He can verify the link address, and he can send that on northbound to the rest of the data center or indeed to the world. TOR B knows he should drop those packets because they have the wrong destination MAC address. However, he can be sniffing those packets all the time because he's receiving them in any case, and he can use that to monitor TOR A's health. At the routing layer, one key to making sure the solution converges fast is to ensure that the convergence scenarios are as local as possible. And so in this case, you have a server all the way on the left with an IP address here, 10.0.0.2/26. You have two TORs, an active TOR and a standby TOR. And as you can see kind of in the bottom middle, both of those TORs are going to do the same BGP announce. So they're both going to announce an equally valid route to that server. And so at the next layer up in the switching at the leaf node is going to see that either of those TORs is a valid route and indeed is going to land traffic, southbound traffic, about 50-50 on those two TORs. Half of it will go to the active TOR and half of it will go to the standby TOR. And so the active TOR traffic is great, no problem there. The traffic that arrives at the standby TOR needs some special treatment. So let me show you how that works. So what we do in that case is the traffic that lands at the standby TOR is received. It is then encapsulated with a VXLAN tunnel, bounced back off of the leaf node, and then sent on to the active TOR where it is decapsulated. And so it basically does an additional hop, which happens pretty fast in a data center, takes about a microsecond or so. But the reason we do that is the leaf nodes then do not have to participate in the convergence scenario. The leaf nodes are perfectly happy to send the traffic to either or both TORs, and the TORs figure it out and get it to the correct location to send it southbound. This allows us to converge very, very quickly, which was the design point of this solution. So let's look at some failure scenarios. How does this thing recover from failure scenarios? So it turns out that actually the most important scenario is planned maintenance. That's often the case. And so we're operating a system, let's say TOR A is the current active TOR, and we need to do some sort of an OS upgrade, which can't be done in a hitless way or hardware replacement or something else. So in this case, the system's running away. You actually have TOR B, which is the current standby TOR, proactively issue a command to the cable in order to switch the MUX. So as soon as the cable switches that MUX, and it happens very quickly, the pings from TOR B begin to then progress through the switch AEC to the NIC. The NIC learns the new MAC address of TOR B and begins to tag its traffic with that MAC address. And so TOR B then starts to receive valid ping responses and valid traffic. He tears down his VXLAN tunnel to TOR A, and TOR B has now taken over as the active TOR. That whole thing happens in less than 100 milliseconds. TOR A similarly sets up a VXLAN tunnel and is ready to send traffic to TOR B, or indeed TOR A can be taken offline. So this is kind of the simplest of the planned maintenance scenarios, and it comes together very, very quickly, typically in about, in less than 50 milliseconds. A more challenging failure scenario is a hardware failure or a link failure. And so, so let's imagine TOR A is active, and TOR A experiences maybe a power failure or a cable cut or some sort of a hardware issue. So in this case, the cable itself can detect a loss of link to TOR A. And so the cable can auto switch on link failure in less than a microsecond. And so when the cable auto switches, you have the same scenario. The pings from TOR B start to get forwarded through the cable. TOR A is now blocked in this case, so the TOR A traffic is terminated. The TORs learn the new structure and set up and tear down the VX LAN tunnels as needed. The NIC learns the new destination MAC address, and TOR B assumes the active role. The whole solution converges in less than 100 milliseconds. The complicated case here is really the TOR forwarding failure. So this is kind of a gray failure, typically a software failure that happens inside of the TOR. It turns out that there's actually quite a few scenarios here, and you can take a look at some of the Microsoft docs on this. So in this case, what we're doing is we're allowing this sniffing function to take over. So TOR B is always sniffing out packets that are being broadcast northbound from the cable, because TOR B is seeing all of the traffic. And so if TOR B times out or decides that the traffic in TOR A is unhealthy, he will take over. So he initiates a manual switch of the MUX inside the cable. His pings then go through, TOR A is blocked. The NIC changes the destination MAC address, and you have TOR B taking over and convergence in less than 100 milliseconds. So all of this functionality is fully upstreamed in SONiC, and the 50 and 100 gigabit versions of the HiWire switch AEC are general availability now. We demonstrated the 200 gigabit version of the switch AEC at Open Compute in November, and it is available in samples now. And so the software will support any SONiC hardware. It supports hitless firmware updates from any cable end. It has quite a bit of advanced cable telemetry, loopback, gated bit error rate management, debug, other functions that we've not previously put in cables. We're also working with a couple of other network OSs. So Arcus, which is a network OS that focused on the telco markets, has OS support for the switch AEC now, and they're engaging customers. And we are working on Cumulus for the NVIDIA ecosystem, and that support is in development, and we will hopefully have some good news on that in the coming months. So Lucas, maybe I could turn it back over to you here.
Yeah, thank you, and really appreciate. I'm sure that we will have some questions. I see already some questions being arrived, so there will be a time. Really appreciate who shared that. I even take a few notes, and I have a couple of my own questions for sure. So just give me a while. So. Don't appreciate. I believe that what you are doing, it is just fitting also perfectly to our strategy as a STORDIS. So as you remember, we've been focusing on the open networking from basically 2014. And speaking about the SONiC, we've been watching that whole evolution from basically beginning, and especially the last year and this year. We saw a lot of deployments, even here in our region. So I believe that Dual TOR is some kind of like a game changer. So maybe even before we will go to the official question, you mentioned 100G. This is definitely something available, and you are working on something new. But how about going a little bit one step back, maybe like such as Dual on the 25G?
Yes, so technically possible, and indeed the hardware that we have in place would certainly support 25G. We just haven't had a request for it yet. So the initial focus was on the cloud makers and who tend to be pushing the features and the speeds quite high. But obviously the capability to go slower does exist. So if we've got some interest, it's something we can absolutely look at.
So I'm sure that if you will find like an opportunity with a few thousands, then you will consider that, yeah? Sure. So our target as a STORDIS is really to provide a complete solution. This is why it is really a pleasure to see what also Credo is adding from the redundancy and special active copper cables. We as a STORDIS are capable to also provide basically any kind of the support. Speaking about something simple like the hardware replacement, but also even going to the software itself, level 1 and 2 on the Sonic. This is something that we will share in more details pretty soon. But again, I'm delighted to be once again with Don and Credo, because this is really making the whole Sonic story, and not only, because we saw that there is also some cooperation with the other NOSes, really complete. So going to the question, I've been making some notes and also took a look on the chat. So Don, if you could share some feeling about the cost, comparing, let's say, that technology with a dual TOR and your cables to, let's say, regular deployment. Yeah. How do you see that? Is that something that you can roughly share in some way?
Yeah, sure. So if you're going to do a dual TOR, you obviously have to have 2 TORs in any case. An MLAG solution requires a 2-port NIC, which costs a bit more than a single port NIC, and then it requires 2 cables for each of those ports up to the TORs. The switch AEC allows you to do it with a single port NIC and then, of course, the single cable. So the net cost of those solutions is quite similar. So what I'm saying is the cost of the switch AEC is approximately the cost of the 2 cables plus the cost adder of going to a 2-port NIC. So for an end customer, this solution does not materially change the cost of it, but obviously it adds the value that we talked about in terms of simplicity and convergence.
Okay, got you. You've been mentioning a few times about the conversion time, but why exactly MLAG is taking, the conversion is so long comparing to your cables and the switch AECs?
Yeah. So MLAG is typically sending a health signal back and forth at a minimum period of about a second, and it doesn't even take action until it misses 3 of those. So it sort of takes 3 seconds for MLAG to figure out that there's a problem. And then the convergence scenario is fairly complex because you have to coordinate between the TORs, between the leaf node, and then between the server itself to get all 3 of these systems back in sync. And so that usually takes about 5 seconds. And 5 seconds is a lot faster than sending a tech out to the floor to plug and chug something, but it's nothing like 50 milliseconds. It's not a cloud scale or a cloud performance of convergence. And so because ours happens much faster, we're measuring health every 10 milliseconds, and we're restricting that convergence to the rack itself, we can do it about 100 times faster.
Perfect. Could you also remind, so the current portfolio on those dual TORs is, as I remember, 100G. We've been just discussing about the potential 25G, if there will be like a, good requirements coming from the market, from the project perspective. But how general you see your roadmap on those, let's say, special product line?
Yeah, sure. So, we're obviously very market driven, and we initially focused this on the needs of Microsoft, which went from 50 to 100 to eventually 200G. We've certainly engaged some other customers, and we've seen that 50 and 100 actually ends up being a bit of a sweet spot for them as well. As you dig into the kind of the cost of NICs, they don't tend to change dramatically between 50 or 25, 50, and 100. And so that's been a sweet spot for us. But if there's a market need to go to other speeds, it's something we can absolutely look at.
Thank you. And the questions from a day. Anyone on the horizon from the NOS perspective? We started from the Sonic. You mentioned about the Arcus, Cumulus, NVIDIA. We remember the acquisition. And anything that you can share and disclose?
So those are the 3 that I can share. I think most of the proprietary OEM NOSes certainly have the ability to support this, but they're going to be driven by their end customer base. And so we have talked to them, but if there's a need inside of a proprietary OEM OS, they will address that. There's unfortunately very little we can do from the outside to build that ourselves. I think the wonderful thing about these open OSs is that the community can actually build the support in. So we can actually do the work, we can contribute it, and then the maintainer's happy to receive that, and everybody benefits from it.
So when there was a question about this, let's say, open software proposal, but that, you're right, it's already triggered me, and I'm wondering how long those traditional guys will be thinking before they will go to you for such as integration, yeah? Because come on, okay, we saw a lot of MLAG challenges, yeah, and especially between the different OSs, yeah. In legacy, in open networking, always, it is a challenge. This is why we have MLAG, CLAG, and so on. Mm-hmm. Here, it seems that the whole complexity is just going away.
It's a much simpler and more robust solution. And I think the most important thing is it allows for a beautiful separation of roles. You don't have to have software running on the server and on the network doing this. Everything can just be moved to the network where really this problem belongs. The compute devices can do whatever they want.
Absolutely. Really appreciate it. So I don't see any other questions. I also went over my notes. Once again, I appreciate Don. I hope that we will still have a pleasure to discuss about something new and exciting coming soon. Just maybe to remind, like always, we have some handouts available on your right corner. And once again, appreciate your time. Thank you for everyone who's been watching us, and see you next time.
Thank you so much. Thank you, Lucas.